Okay, boys, we're back for a wee bit more story, dog and pony show for the clamp on ammeter series and waveform interpretation when it comes to DC brushed motors. I've actually got my same fan assembly here. You can see it running here, boys. Now this is a variable speed fan. As I mentioned, it's from a Vitara, a climate control blower fan. So I've got it only operating at 5 volts at the moment. You can see it's drawing 2.5 amps-ish, just over 2.5 amps, 2.6 amps, whatever it is. Just so that the noise is at a reasonable level. But it really is neither here nor there with respect to the demonstration, boys, right? Tonight's dissertation is really on appreciating the fact that there's, although it seems very simple and very obvious, there's two sides to the motor. There's the electrical side and there's the mechanical side, what's actually being driven. Both of them can skew the waveform. So tonight what we're going to look at, and I should have made this part one, I'm sorry I didn't make this part one in hindsight. We're going to look at the simple notion of how the waveform is actually affected by the load on the motor. Whether what we're looking at as far as an anomaly in the waveform is an issue with the electrical side of things, or is it an issue with respect to the load that's on it? Is there an issue with the blower? Is there an issue, is the blower binding? Is the bushings gone in the motor? Is there something mechanical that's causing essentially a form of drag, or completely, or at least partially or completely losing the load entirely, right? So I've got the waveform actually up there active at the moment, boys, and as you can see, and you can see the current draw there actually on the I've got it on the measure function here. You can see it right here, boys. So here is the nominal waveform, and it looks very much like we've seen in part one, if you recall. It is in fact a 12 segment motor assembly. I confirmed that visually by actually inspecting it, and I'm going to keep it really simple tonight. And as I said, this should have been part one, because you will see a distinct change in the current draw and on the waveform that's actually presented when there is an issue on the mechanical side of things. That's essentially what the focus of this particular part is. All I'm going to do is actually use this little rubber vise jaw I've got and actually put a brake on the motor. Right, so what we actually going to see, just for simplicity at the moment there, boys, look when I put some drag on the blower, watch the current. The speed goes down and the current goes up. We're excessively loading the blower, right? We've got 12 humps on the waveform. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, you can see actually quite clearly the small one there with a little peak, let's call it, and then the small one there with a little peak. So let's actually take that reference point right there and we'll go over. Okay, so there's the time there, boys, of our reference. That's just with the fan operating completely normally. You can see there I've taken the measurement, and if you recall, it's similar to the measurement we had the other night, 39.3 milliseconds. So 60,000 divided by 39.3 equals, that's 1526 RPM wise. So if you recall the formula we went through the other night. Apply the brake. You'll notice the current line will actually jump up. You can see on the measure I've actually got on screen. Okay, so that's good. Let's hold that right there. The first thing that you're going to actually encounter when you're actually using the current clamp and checking to see the current draw on a motor, if you have a baseline to compare it to. Now, if you don't have a comparison, baseline to compare it to, this is going to be difficult to actually realize that this is drawing excessive current. It's always good to have a baseline. I mean, ideally, you'd have a reference for everything that you potentially will be dealing with. If I'm a millwright and I'm in a factory, there's lots of drive motors in a conveyor belt assembly or something like that I'm dealing with. Ideally, I would have, when things are operating normally, I'd take a snapshot, keep on file the baseline, so I'd have this facility available to me, so I could see that, hey, there's a bearing going out on this drive belt, or whatever the case may be. Maybe there's a bearing in the case of this fan. There's a bearing that's starting to seize. There's an excessive load on it. How do I know that? Because I now have elevated current. As seen before, it was 2.4 the nominal draw. Now you can see the nominal draw has actually gone up to 3.3. Not only that, let's see if I can do this statically here again here, boys. We'll do a measure. And you'll notice that our time has actually gone to 42 milliseconds as opposed to the original 39 and change. Sounds insignificant, but let's do the calculation on the frequency. So again, 60,000 divided by, in this case, 42.1. And the frequency has now dropped actually almost 100 hertz. It's now 1425. What did I say it was originally? 15 and change for sure. So around 100 hertz drop. So basically, if you have an excessive drag, that's exerting itself on whatever motor it is you're actually testing, you're going to see two effects on the waveform. You're going to see an increase. It'll jump up in amplitude with respect to current, right? Because there'll be more current drawn as the motor actually slows down. Motor slows down, less back EMF, more current, right? And you'll also see an expansion in the waveform with respect to the timeline, because of course the motor is actually slowed down. We've gone from 39 milliseconds from one segment in the commutator to a full rotation to 42. What did it say? 39 milliseconds to 42 and change milliseconds. So, and 100 hertz-ish change in actually rotational speed. So that's effect number one, excessive drag. You're going to see those two effects, increased current and expansion of the waveform. So let's consider the other situation that you might actually encounter. It's at the same settings. It's still 5 volts, and now you can see we have a nominal current draw of around 1.4 amps. So as you can imagine, the waveform has actually dropped on the screen significantly. So we have a significant drop in current draw. So what scenario do you suppose is actually going to cause that? And I'm sure you can hear on the soundtrack, we have a distinct change in what we can actually hear with respect to the blower noise. Why is that? Because we have no blower. There's nothing but a little piece of tape on there, so you can actually see the rotation of the shaft on the motor. So you can see with the motor unloaded, there's going to be a significant drop in the current draw. Hence the drop on the trace on the scope, and hence the drop with respect to that's actually the mean current that is actually measuring on the measure function is showing in the bottom left hand corner there, boys. So in addition to that, if I have any idea what I'm talking about, there should actually be, as opposed to an expansion of the waveform segments, boys, if you had excessive drag, now we have no drag because our load is completely disconnected from the motor that we're actually driving from. There should be a compression. There should be a significant increase in the speed. I don't know about significant, but there will be an increase in the speed if the theory holds true. Our cursor measurement details, you can see here that our delta T is actually 36.9 milliseconds. So not only do we have a significant drop in the current, but I believe we have a compression in the waveform. Let's check the frequency. Our baseline frequency, if memory serves, was 15 and change, 1525 or something, right? Let me do a quick calculation on this. So again, 60,000 divided by 36.9, and that actually equals 1626. So we have about an increase of about 100 hertz in the rotational speed, or 100 RPM of the, not hertz, let me get it right, 100 RPM increase of 100 RPM in the motor that's now completely unloaded. So kind of counterintuitive, right? We have an increase in speed and a decrease in current draw. Not counterintuitive if you realize these are the hallmarks of an unloaded motor, right? So it could be anything. Maybe there's a shaft that's sheared somewhere. Maybe the pump that was actually driving this has now developed an internal bypass of some sort, or the pump element is actually slipping on the shaft. Something is unloading the system. It's a sure sign that the system is being unloaded if there is a drop in the current trace and a compression of the humps, the waveform, i.e. there's an increase in speed in the system, right? So that's it for tonight. We've been looking at essentially symmetrical waveforms. What's the story when you start to have asymmetrical waveforms? What's the story there? What's potentially the issue? We can discuss in upcoming parts. So I hope that made some sense to you, boys. I'll leave it at that.